Okay, so far we have learned how to integrate by just the power rule, x to the n plus 1 over n plus 1, and we've learned u-do substitution. When you take calculus in college, when you get to Cal 2, you'll learn one or two other ways to integrate, and we still have a couple of rules for ln and e to learn. But there are some problems that we cannot integrate by normal means. By that I mean, in theory it can be integrated, but there's no algebra that will allow us to integrate it. So we have to come up with approximations to that. And we learn to integrate, what we mean by that is we learn to integrate it numerically. Meaning we're just going to get an estimate to it. Now we've already done some of this because where did we start off at with integration? What were we doing? Riemann sums, and Riemann sums were just approximations. What we're going to learn today is two better approximations for finding the area. We're going to practice that a little bit. So it's just really a matter of being able to use some formulas here. So let's start off by looking at this problem and look at the directions there. Approximate the area by finding the area of the trapezoids. Now, there are 4 trapezoids here. Okay? And y'all are going to say, what? Because 1 and 4, what would you really call them instead of trapezoids?
Triangles.
Triangles, okay? It's okay, but hold on just a second. Okay, so we said, even though they really are triangles out at the end here, I'm going to use them as trapezoids because we can work it the same way there, and you're going to see problems where you need to think of them as a trapezoid. So, before we go further, who can tell me what the area of a trapezoid is? What's the formula? Uh-huh. Oh. Mm-hmm. Divided by 2, okay? All right, so that's the area of a trapezoid formula. You learned that somewhere back along the lines, forgot it, and we've talked about it again, you forgot it. So now maybe you'll remember it here, okay? It'd be a good thing to try and remember here. Okay, in this picture, what is our base?
The distance between like 0 and pi over 4.
Yep. These things, yes, the x-axis, these are our bases, and these here, I said that, no, y'all said that wrong and I agreed with you. My apologies. Okay, the bases are these things, here, 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 and here. This is our height, okay? And we talked about this before. I know that you're like saying, well, what? The height is how tall it is, okay? A normal trapezoid looks like this, okay? Where this is our height, this is one of the bases, this is one of the bases, okay? So can you see that what we've really got right now is trapezoids that are turned 90 degrees. If this is what your normal trapezoid is, we've got them turned 90 degrees here. Okay? So, now, let's talk about, and we're going to do this the long way here, the long way, to see if we can learn something that will help you to put all this together easier for future problems. So, talk to me about the area of the first trapezoid. What's the base? What's the?
0.
It's 0 plus, how tall is this?
Pi over 4.
Yep. Sine of pi over 4. And I'm going to write it like that. And really, that's 0, but it's the sine of 0. Because it's the function value evaluated at 0. And I'm going to write it like that to help you see something here, okay? Times, what's the height of this thing?
Pi over 4.
Pi over 4. And how did we get that height of pi over 4? because we're talking about the distance from here to here is 0 to pi over 4. The distance from this point right here to this point right here, pi over 4 minus 0 is pi over 4 divided by 2. Agree with that? Now, so write down what the second one is. The area of the second, in the same terms there. What are the two bases?
Well, the first one would be sine of.
All right, and the second one?
Would be sine of pi over 2.
What's the height? Divided by 2. Y'all, is anything kind of flowing through here? So what's my next one going to be? And the last one is pi. Okay, so, and to approximate that, we just find out what each of those numbers are, add them together, right?
Yes.
Let's see if we can find some common stuff. When you look at those, what do you see in common?
Pi over 4.
Pi over 4 is in each one of them. What else do you see in common? Oh,
The first thing is the one that was on the second one was the diamond 4.
okay. So I see pi over 4 is common to all of them. I see that divided by 2 is common to all of them. And does everybody see what Madeline just pointed out? The last one in A1 is the first one in A2. The last one in A2 is the first one in A3. The last one in A3 is the first one in A4. Okay? Now, I know this is going to be long, but I want us to not use our calculator yet. Write that down just like it is and do some algebra to simplify it. So we're not going to say the sine of 0 is 0 and the sine of pi over 4 is root 2 over 2. We're just going to do some algebra to clean this up, okay? So let me start off by writing it out for you here. So our, well, we're not going to distribute. Yeah. Watch what I'm going to do here. Yes, we're going to do some factoring, hopefully, okay? All right, the first one we said was sine 0 plus sine pi over 4 divided by 2, and there's a pi over 4 out here. Plus, then we've got the sine of pi over 4 plus the sine of pi over 2 times pi over 4 divided by 2. Plus sine of pi over 2 plus the sine of 3 pi over 4 times pi over 4 divided by 2 plus oh so, what can I factor out? Pi over 4 and a 1/2, okay? And so I'm going to factor them out that way. So the area, we've got a 1/2, we've got a pi over 4. Now, what's going to be left in the first one?
Sine of 0 plus sine of
And what's going to be left in the next one? Okay, all right, so let's write that out. Hopefully you're about to see something. Almost. That would be even better.
Oh, well, they're next to each other, so you can make like two signs, blah, 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 blah.
All right? And yes, now we've got some like terms in here. Boom, boom, boom. So you're right. We can clean this up a little bit more, and we can get that the area is approximately 1/2 times pi over 4. And I know I can multiply those together, but I want to keep them separate for another reason here. Sine of 0 plus 2 sine of pi over 4s plus 2 sine of pi over 2 plus 2 sine of 3 pi over 4 plus the sine of pi. Okay? So, can you simplify for me in words how to find the areas of those?
1/2 pi over 4 times.
And pi over 4 is the height. All right.
Well,
So
1/2 times the height.
what happens in here?
The ones that are in the middle and not on the outside, there's two of them.
There's 2 of all the ones on the inside and only 1 on the outside. Does everybody see that? Now that's the trapezoidal rule that we just quasi-created here, okay? If we are trying to find the area, one thing you could do is go and find each of the trapezoids like that, okay? Like we started off up here. And if it's just 3 or 4, it might not be that bad. But what if there were 6 trapezoids there? It's just a lot of work to a lot of stuff. And more than writing it out, there's a lot of places to make mistakes punching that on your calculator. Because you've got to punch pi over 4 right 4 times and divide it by 2 and get all your parentheses right. It's just highly likely that you're going to mess something up. Punching this on your calculator, you're much more likely to get the right answer. Wouldn't you think? So, that's the trapezoidal rule in a nutshell. Okay? It's going to be 1/2 the width. Now, let me say this. You're not going to hear it. You're not going to remember it, but I'm going to say it anyway. The width has to be the same for each trapezoid in order for this to work. So if up here, if I did not have pi over 2 and I was just using one from here to here, I could not use the trapezoidal rule. If I had the same curve and I had one here and one here, and I've only got 3 like this, notice the one in the middle is far wider. Agreed? Cannot use what we just developed. You've got to do it the long way by finding the area of that trapezoid, the area of that trapezoid, the area of that trapezoid. Seldom will you see that, but I'm telling you anyway. Don't do it unless all of the trapezoids are the same width, okay? Width's the same. The first function value, 1 time. 2 times all the others. The last function value, 1 time. Is that complex? That's not complex, is it? Okay? So, see if you can do it with that one there. Do it out just like we just did. You're going to have to use your calculating device. You'll have to use your calculating device. I'm going to give you a moment to do that while I try to find something. Yes. There you go. You're welcome. Okay. That doesn't do what I wanted it to do. So let's see if I can find one that does. Ha 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 ha.
You just got your calculator and they've been touching the first for like 5 minutes.
$1.97.
That's what I got.
Good.
That's the bunch you got. Each a bunch of numbers. Why is there a sigma in there?
Because we're adding them all up.
Okay. Oh yeah, sigma notation. We did that
Yeah.
last year.
Okay. 1.97 is what this machine up here got. I know you're not finished yet, but some of you, if you get to that, you should be good to go. Should be able to do that with your calculating device, okay? If you can't, you are in trouble.
I got an answer.
What'd you get?
I got 3.22.
Wow.
Multiply it by 1/2 and pi over 8. Okay.
Let's see.
Which is really close to 1/2.
Uh,
3.4.
well, let's see. All right, let's see. I see sine of 0 plus 2 sines of pi over 8 plus 2 sines of pi over 4 plus 2 sines of 3 pi over 8 plus 2 sines of pi over 2 plus 2 sines of 3 pi over 4 plus...
Oh, I forgot 5 pi over 8. I skipped one.
Okay. But that shouldn't matter. 4 pi, yeah. Yep. Okay.
Yeah, that would
All right, so you said you needed 2 sine of what? 5 pi over 6? No. 5 pi over 8. 5 pi divided by 8. And then after you did all that, you did what? What'd you have to do next? Times pi divided by 4?
Mm-hmm. 25 4, and then times 1 half, or do I?
Since pi over 8.
Ah, yeah.
Pi over 4 is pi over 8.
Oh, because it switched.
And then you get the right answer. Okay. All right, is everybody comfortable with that? Okay. I'm going to send you this website in just a few moments. Notice this is a website that I just found in the last 6 or 7 seconds here. That if you go here and type in your function, type in where you're going from and to, the number of intervals, how many of them do you have? 1, 2, 3, 4, 5, 6, 7, 8. Okay? You type that information in and poof, it'll give you the answer, okay? I'm going to send that to you mainly so you can check yourself. No, you could not use that on your test, but you could use it for other things, checking to verify that you've got things right there.
I figured out how to program my calculator to do that.
Which you can do rather easily. I'll have to get back to you on that.
Well, I don't know how.
Yeah.
Just...
I'll have to get back to you on that. Okay, so remind me in a little bit to send that to you. Okay, so that's trapezoidal rule. All right? Now, look at this ugly thing here. That's what you've just been doing, okay? That's just poof. You're never going to be asked to throw that out, but that's poof what you just came up with. Yes, sir. Do not. Do not. So, where did they get this b minus a from? That's the two ends. That's the endpoints from 0 to pi in the example we've been working. What is n? The number of intervals, the number of trapezoids that you have there, okay? So, this is what we've just been doing. You'll see it. It looks impressive, but it's just what we've been doing. So, this is one that the Simpsons rule is one that we're not going to come up with. We're just going to say, poof, here it is, okay? Poof, there it is. Okay? Let's talk about where everything came from, and then we'll work through an example here. What do you see that's different about Simpson and trapezoidal? 3n in the bottom as opposed to 2n. Okay? The n ones still are 1, but the middle ones go between 4 and 2. 4, 2, 4, 2, 4, 2, 4, 2, 4, and it always has to end in 4. Okay? So, what does Simpson's rule do? It just gives you a better approximation sometimes. For your purposes right now, we'll either say use trapezoidal, use Simpson. So you just got to know which one to use. Plug it in, spit it out, poof, there it is, okay? So let's look at an example with Simpson's rule. Okay? Now we're going to focus on n equals 4 to begin with. Notice we don't have a picture this time. Okay? No, it says use Simpson's rule. It says use Simpson's rule. So let's try to take this thing, edit, copy, come over here, and can we use this and just write it out without having to draw a picture here? Well, what's our A and what's our B? All right, so we've got pi minus 0 over 3. And what's our n? 4, because we're going to do that one to begin with there, okay? Now, how are we going to figure out these x's in here? All right, well, the first one is where we're starting. So we're talking about the sine of 0 plus 4. What's going to be the function value we put in the next time? Pi over 4. Is everybody comfortable with that? How do we get this? How do we get pi over 4 right here? Well, it's pi minus 0 over n. Because, all right, what in your head, think about what the graph would look like. There's a sine from 0 to pi. We said we're going to break it into 4 of them. All right, that breaks us into 2, 3, 4. So if that's pi and that's 0, I got to think about what those would be. Yeah, make it into fourths. If it was eighths, we'd make it into eighths down there, okay? So it's going to be pi over 4 there, plus 2 sine. What's going to be the next one after pi over 4? Pi over who? 2. How did you get that?
Pi over 4 plus pi over 4.
We're going up from this one that far, pi over 4. We're going from pi over 4 up pi over 4 to get to that one, okay? Plus 4 times the sine of 3 pi over 4 plus the next one's going to be pi. So we're at the end, so it'll be the sine of pi. We figure out those 4 things multiplied by pi over 12. Can you tell me what the answer should be approximately based on what we did a while ago? What answer did we get a while ago? 1.97 or something like that? Okay, so we would expect to get something around 1.97 again, okay? You you can punch on your calculator. You can figure that out. I'm not going to take our time to do that. If I just gave you this problem right here, if you saw on a test, integrate 0 to pi of sine x, what would you do?
Integrate it and then plug and subtract on this. But I guess you could assume.
If you just, for some reason, 5 years from now, somebody says, hey, I'll give you $1 million if you can integrate this problem and get the answer. Exactly. You would just integrate this by using algebra, wouldn't you? Derivative of negative cosine is sine, negative cosine evaluated at pi and 0, and I'd get 2. Remember, we're using this right now as an example. When you're posed with this problem, this specific problem, any problem, unless you're specifically told use trapezoid, use Simpson, you always try to do it algebraically first. Algebra is going to give you the exact answer. This is only an approximation, because if you do this algebraically, you get 2 for an answer.
You get 2.00455975.
So we get 2.004 here. We got 1.974 a while ago. So you see they're both, if we did 8 here, I bet you'd get 2.000 something there. So they're getting close, but none of this that we're doing today, numerical integration, will never give you the exact answer. All it's going to do is give you an approximation to the answer. Okay? Clear on that? Okay. So trapezoidal rule, use that formula. Simpson's rule, you use the new formula we just gave you. Now let's look at this problem here. Only a couple more to look at here. Approximate the area of the shaded region using trapezoidal rule and Simpson's rule. Okay, so we're going to do trapezoidal rule first. Okay, n equals 8. All right, so if we're doing trapezoidal rule, we know it's 1/2. How wide are each of our trapezoids? We've got n equals 8. So where are they at here? 1, 2, 3, 4, 5, 6, 7. It's going to be 1 each. Except it says with n equals 8. Yes, you could do 4, but we specifically says n equals 8. So that means your width here is going to be 1. All right? And what do we know about our function values in here? I mean, the first one, what's the first function value? What's the first number we're going to put in here? 0. Why 0? Because this thing starts at 0 here, okay? What about at 1? What are we going to use? 2 times, what do you want to call that to be? All right, sounds good to me. 1.2 plus 2 times. It looks a little bit above 1 to me. Yeah, we're not looking. Yeah, we're just looking at where this dark black line here crosses at. Okay, so see at 2, what are you going to call that function value? I think that's 3 plus 2. The next one, when we get over to 3, that's, call it 6 maybe?
Yeah, can we just get close to it? It's not going to be accurate anyways.
Well, close, yeah, as close as you can get. Like 4 looks like it's up there at 9. 2 times 9 plus 2. The next one looks like it's at 10. Plus, the next one looks like it's at 9 again. Plus, the next one looks like it's at 6. Plus, and the last one's at 0. Okay? And now it's just add up a bunch of numbers. 12. So we've got 1/2 times 2.4. 2.4 plus 6 plus 12 plus 18 plus 20 plus 18 plus 12. 18, 30, 50, 60, 70, 86, 88.4. Anybody else get that kind of number? Okay, good. That's an approximation of what the area would be. Now, you do Simpson's rule on your own. See what you can come up with.
It is 1, 4, 2, 4.
Yep, 1, 4, 2, 4, 2, 4, 2, 4, 1.
How many it takes, and you have to start and end with 4.
Right.
It starts with 1 and 4, and then ends with 4 again.
Exactly.
You want to solve it out?
Sure, let's go ahead and get a number out of that.
How did you do that in your head?
I really don't know.
Because that's exactly what it is.
Just got lucky. I get that way sometimes. All right. So now, last thing I want, last problem before we get there. Golfers. When you go to the golf course, do they tell you how big the greens are? I mean, some golf courses say it's a certain area, right? How do they figure that out? Are greens rectangular? Very, very odd looking shape. How on earth do they figure that out? They do something like this here. Okay? Or one day each of you will more than likely want to buy land as well. When you buy land, you'll buy so many acres. Guess what? It's not in a square. It's in some odd looking shape, okay? Now, in some places, it is relatively close to squares, but most of the time, it's going to be some funny looking shape. How do they find the area for those things, okay? They do something very similar to what we have just been doing here by approximating it. Now, no, they don't go out there any longer with paper and pencil and measure stuff and write it down, but they do get some measurements and then put it into something that uses exactly what we've been doing and calculates the approximate area, okay? Now, this is a problem that you want to be sure and put a star by because I can almost guarantee you that one like this will be on the exam in May. Because it looks so easy, it tricks up students. Because they look at it and say, oh, I know exactly what to do. Okay? And you do, but you just have to be careful. You cannot use the trapezoidal rule always on it. Sometimes you have to go back and actually do the trapezoids. Okay? Here's what you're looking for. Our height is with our x's or with our y's? With our x's, okay? Glance at all of your x's. What's the difference between any two consecutive ones? Is it 100 for every one of them? It is. Therefore, we could use the trapezoidal rule here, okay? Since the difference between x is xn plus 1 minus xn is always the same, you can use the trapezoidal rule. If they're the same. If they're not the same, you cannot, okay? We're going to do this one here with the trapezoidal rule, then I'm going to make up one off the top of my head that we can't do that with, okay? So, we don't need, do we need to wade through this? I mean, it's just plug numbers into your calculator. You're smart enough to do that, right? Let's look at this data set then, okay? Our time, okay, we've got a car. Car's going down the road, and at these times, we're going to measure 10, 20, 40, 60. All right? And we're going to measure its speed at these specific times, okay? It was going 20 miles an hour, it was going 28 miles an hour, it was going 40, it was going 30, and it was going 40. Okay? So if you got clear in your mind, okay? You're sitting there, you are timing, and when you started timing, somebody took a gun and shot, and the car was going 20 miles an hour. 10 seconds later, they shot, and he was going 28 miles an hour. 20 seconds later, 40. 40 seconds later, 30. 60 seconds later, 40. Okay? How far has he gone? Is the question. All right? So now let's look at what the question is, how far has the car traveled? That's the question. Okay? Now, I know we're integrating right now, so it sounds logical that we integrate, right? Otherwise, Mr. Ely wouldn't throw this at us. But why is it integrating? We got speed.
We did stuff like this before too, like with the boat, where it was going at a certain speed and you timed it at certain places. So to figure out how far it had gone, you use those two things.
Yes. Think about a couple of things here. Think about it back to Algebra 1. Rate times time equals distance. Here's our rate, here's our time. But what we're doing more exactly is we're integrating this. We're integrating. These are our x's up here. These are our y's down here. Okay? Now, our x's. Is the interval the same all the time?
No.
It's not. Okay? So then, when we've got to look at, we've got 4 intervals here, I think. 1, 2, 3, 4. And we've got to see each of those 4 as a trapezoid, okay? Each of those 4 is a trapezoid. How wide is this one? 10. What do I do with the 20 and the 28? They are the heights of it. 20 plus 28 divided by 2. Okay? That's for this first one. What about for the second one? It's 10, 28 plus 40 divided by 2. Does everybody know where the divided by 2 is coming from? Because that's area of trapezoid formula, okay? What about the next one? 20 40 plus 30 divided by 2. And the last one is 20, 30 plus 40 divided by 2. Easy problem. But if you look at it and say, oh, trapezoidal rule, it's going up by 10s, 1/2 times 10, one of those, two of those, and one of those, you get it wrong. Okay? That's what's going to be on the exam. That one right there. This one won't be.
Question.
Yes, ma'am.
What if, would your answer be drastically different if you went from 0 to 20, 20 to 40, 40 to 60 and made 3 trapezoids? So then they were all 20.
Yes, and it's going to depend upon the question. Okay? We would say something like using 4 subintervals. What does that mean to you? Use 4 subintervals.
Make sure you've got 4.
You got 4 of these. Now, if I said use 3, yeah, you could do 1, 2, 3, and then they'd all be 20, and you could use a trapezoidal rule. But most of the time, we're going to specify use 4. And just as a practice, you want to get the most accurate answer you can, so you want to use the most data you can. All right? So that's just a punch buttons and add up numbers problem there. Simple to do. Agreed? Okay. I'm sorry, that's all I have for today.